Pleasure to have Marc speaking to us today. Marc is a physicist by training, undergraduate and grad school. He did his PhD in theoretical physics from the University of Göttingen. And then he held several research positions around the world before starting his own research group at the Max Planck Institute in Göttingen, where he was for about 8 years. And then he has moved to Dresden to hold his own chair in network dynamics at the Technical University of Dresden. Marc has been extremely prolific, publishing in very different areas, but always with this common core of modeling. And he has published in excellent journals in numerous times, including those from the Nature, Science, and Physical Review Letters table. So we are really looking forward to his talk today on inverse problems in network dynamics and estimating network structure from data. All yours, Marc. And if you have questions, feel free to write them in the chat as usual. Yes, Marc, yours.
Yes, thanks so much, and everyone for coming and for having me today. If you have questions, as Suresh just said, you just can either write them or speak up if you want. Today I'll talk about inverse problems. I shouldn't have clicked. Inverse problems in network dynamics, and I'll shortly explain in a few slides what I mean by that. And network dynamics, the phrase here is just a placeholder for high-dimensional dynamical systems. So I want to talk about how they operate and whether they can be deterministic or stochastic. They can be discrete in time. They could be discrete in space in principle. And today I basically focus on continuous descriptions, so systems you can describe by sets of coupled ordinary differential equations. The work I present today is joint work with Jose Casadiego, who was a PhD student and then postdoc with me in, PhD student in Göttingen and then postdoc here in Dresden. I just saw a spelling error. That's Moa Nitzan with an N, not an M. She was at Harvard, now she is at Hebrew University. Joachim Peinke from Oldenburg and Hauke Heine also from Oldenburg. Networks are everywhere and most of them are dynamic. And if you think about your favorite network, you will see that this has a very specific and very important function. This is true for your own natural networks, like social networks. You make friends and you have colleagues you work with, but it's also true for the content of your head, which is neural circuits, the brain, or the content of your cells. For example, gene and protein regulatory networks, as well as, for example, metabolic networks, which is another, you can phrase it as a chemical reaction as well. But it's also true for lots of man-made networks, for example, transportation and distribution networks. Think of the portion of daily water you get off the pipe network, or the electricity powering your computers and your home. Each of them is essential in everyday life, and thus it's important to understand what the collective systems level properties are. In our team, we attempt to understand collective dynamics, and we are serious. As Suresh said, I'm a physicist by training. I studied math and physics, and I'm somewhere between these two subjects and a lot of different application areas. Originally, my training as a PhD was somewhere between dynamical systems theory, like real math, and neuroscience. And from there, I bridged out into different areas of biological applications, socioeconomic applications, and physics applications. And today I'll focus on what I boxed in red, which is motivated by biology, but what comes out is actually pretty general. And you can think of applicability across models and real systems, not only in biology. So a standard perspective in nonlinear dynamics or dynamics in general is, from a serious point of view and also from a modeler point of view, is a forward problem. So you're given a system, you want to maybe fit the parameters, and then you set the condition, for example, the initial condition or other constraints to the system, and then you observe, or you want to find out what kind of dynamics comes out of the system. So you're interested, if it's a network, for example, or a large high-dimensional system, you're interested in the collective features. They could be multi-stable, so several possible coexisting states depending on the initial condition. You could be interested in the fixed points or periodic solutions or chaotic properties of certain sub areas of your state space. And all of these are forward problems. All right, let's term them forward problems. Because you are given a system and you want to understand their dynamics as a function of, for example, parameters. So your system, you have a model of the system, and then you want to find out what the dynamics is. For example, predict it or just understand, characterize it. You can also have a non-equilibrium situation, which in physics is called non-equilibrium because it's like somehow driven. In terms of differential equation, you would talk about non-autonomous systems. You have an external driving force. It can be one-dimensional, like here indicated. It could also be several inputs. So the input here could be like a vector, and obviously it can be time dependent. So in summary, forward perspective is taking a model of a system constituents, like individual units, parameters of the coupling, and so on, and predict or characterize types of collective dynamics. The question is, of course, how to obtain this model if you don't have one. So typically, what I myself did for a long time, and in our group has been done several times, is you go to the literature, you take your favorite model, or you find a model which is relevant enough, and then you investigate that model because there might be an open question, for example, in biology, or we also do mobility research and energy systems like power grids and so on. So, but taking it from literature means you take it from somewhere else, from someone else. And of course, then sometimes you want to add a new parameter or a new compartment to a model and so on. But there's a second way of tackling the question how to obtain a model of a given system. And that's do it yourself, like use the data and try to get features of the model or the entire model if you can. And with Jose, we wrote a pretty mathematical review in Journal of Physics A, which is a theoretical and mathematical piece of Journal of Physics, already in 2014. At that stage, focusing on the novelties which came up because, for example, due to, well, first of all, data, but there are not so many data in the system. It's more about the methods. And the second and important piece of methods is that what came up is, for example, compressed sensing. So there are new mathematical tools by which you can more efficiently determine properties of a system, although by traditional means you would have too little information. So then if you have a system and you want a model, then what you record is data. So you observe the dynamics. You have time series, either scalar or multidimensional time series. In our case, it's mostly about multidimensional systems dynamics. And sometimes these systems also have an input, and you are asking for the system model. So it's the other way around. Observe the system, deduce system constituents, or at least some properties. Which are the most important properties in a network? So if you have a network, you have something like that. You have a structure of units, and they have a set of units, and they have some interaction structure. And they might be directed, they might be weighted, they might have functions attached to it, which mediates the interaction and so on. What are the most important features of such a network? If you just look at my sketch here on the left-hand side, you see, okay, there's one obvious thing which I want to know first, which is how many units does my system have? And the second is, if I know that, what is the interaction? Like, who is communicating with whom, or who is interacting physically with whom? And I address both of the problems today, and first go with the first and maybe simplest problem, which was reasonably overlooked, I think, in the literature for 2 decades. Probably because it wasn't fancy. Network scientists did focus on the structure of networks, and dynamical systems or time series people focused on something like attractor reconstruction, for example, finding the stationary distribution of points in state space and so on. And we ask the simple question, how many nodes, or in more general terms, how many dynamical variables do we need to describe the system? And I will run over a few mathematical details pretty quickly because it might not be super interesting to listen to that for a long time, but I just sketch the main idea, okay? And all the details are there and they're in the paper, and I present them, but I don't go into details. So imagine you have a network, and imagine you can only observe time series, meaning measuring variables, in some of these constituents, some of the units. And these are here shown in color, and others, like those outside the ellipse, are uncolored, meaning you can't observe anything from them. You can't measure those variables. So you have a subset of variables, and you want to know, in the simplest setting, what is the number of variables total in my network? Obviously, you have to satisfy some trivial criteria, like, for example, the network needs to be connected. If it's not, you can't detect nodes which are not connected to those nodes or units or variables which I observe. So you observe some of them, you perceive the dynamics of small n units in a system of capital N units, okay? So here small n is 5 and capital N is whatever, 11. And of course, there might be different conditions, and in some conditions it might be driven from the outside. You can drive it in several ways, for example, continuously in time, or you kick the system to random or to distributed initial conditions, and we'll use the latter, like we kick it at instantaneous times to some initial condition and then do one experiment, measure the response, and repeat that, okay, because it's one of the simplest ones. But we also have some knowledge about what happens with continuous signals. I call the state vector of all units, like here an 11-dimensional vector, x of t, and those which I can perceive, where I can record time series from, y of t. And the question is, what is the number of variables, or in this case, the network size? And this is the idea. So even if you don't like math and have only rough intuition about it, this is the intuition about the reconstruction idea. So reconstruction is, again, you record time series, which are dynamically sampled time series from different initial conditions, and they, for example, they relax. Do you see my mouse?
Sometimes.
So they relax to different kind of states depending on where you start, okay? So you have one experiment here, a second here, a third here displayed, and you collect these data, and I'll tell you in a minute how exactly you collect them. You collect these data, so that's all information you have about the system, into a matrix, and then you increase the dimensionality of the matrix. So do more and more experiments, or if you have a given set of experiments, you just take into account more and more of those time series. And then what happens is the rank of the matrix, typically if the time series are orthogonal to each other or non-linearly dependent to each other in high dimensional space, you would increase the rank of the matrix naturally, but at some point you can't increase them anymore because the total dimensionality of your system is just something, n, a capital N. So the rank will grow, and at some point it will saturate. Very simple idea, but because it's so simple, it's very general as well. So we can apply it to all kinds of situations, as I'll show. And it's still not done, it's just the first step is done. So collect different sample trajectories of perceptible states, suitably arrange them in a detection matrix, which we call T, and exploit that the rank is at most the total number of variables by construction, right? They must be linearly dependent at some point if you are working in a finite dimensional system. So I start to explain the idea. I start with a really simple setting. So linear, noiseless relaxation dynamics towards one unique stable fixed point. So the best ideal mass world you can imagine. You have a nonlinear dynamical system at a fixed point Z star, By construction, the f of that is 0. So you define a perturbation x of t, which is z of t minus the fixed point, and that's the deviation. Now you linearize it, you get a matrix equation with A being the matrix, and the matrix elements are given by the Jacobian of f at the position of the fixed point. Now, because it's a linear equation, you can formally solve that by the matrix exponential function, which you can write down analytically once you have the, well, eigenvalues and eigenvectors at least. And formally you can write down in any case. So you can write down this form. So in other words, you know the solution. The problem is here that you don't know x, right? You don't know x of t because it's a full state space vector. You only know a fraction of the nodes, so only some components of x are known and some are not. So what is actually observed is the observed time series is a projection out of that vector. So In is a small n by n identity matrix projecting out the first n, let's say, components, and the other capital N minus small n components are not visible. So you have no clue about them, okay? Then you can write down formally, again, this equation, which is the framed one. yi of t is the sum over time-dependent coupling functions, which are also time-dependent, and they multiply some initial state. And here, this theta ij is just the matrix element ij of my matrix exponential. The problem is I have no clue, right? I don't know f, thus I don't know a, and I don't know most of the components of x. So the only thing I see is more or less the left-hand side of the boxed equation, yi of t. So and then you observe capital M time series for each of them, for each of the components, yi. Yeah. And you do that in discrete time, right? As you would do in reality as well. You sample at k different times. So again, just a copy from the previous slide. You now collect the different trajectories, m trajectories, into a vector. And now you can collect these vectors for each of the m1s. So sorry. Small m labels the experiment. So experiment number 1 would be m equals 1. You take the vector for m equals 1, which is like a small n-dimensional vector, and you write down this as matrix equation. Now you collect these ones for all the different measured trajectories. So all the experiments you collect in one, you get a matrix which looks like that. It's y of t equals theta of t times x0, where x0 is the initial state vector. The problem again is x of x0 you don't know. And now I construct T, which is my detection matrix, which is a collection of all of these suitably arranged. So I have these double transpose here, but it's really an arrangement of all the time series, as I said before. And then you have this very trivial equation, which contains all the data you have. You collect time series, you arrange them in the matrix, and then for those of you who know the matrix, you can make predictions, okay? Problem is, the blue box is all the information, and it's, you know, it is in the simple setting, it is split into two matrices. Well, two matrices. One is completely unknown. It's a coupling, like it's time dependent and depends on the node pairs. And the other one is partially unknown. X0 is the set of initial vectors. And what is known about it is the components y, like those components you measure, the first small n components. Okay? So problem is essentially the right-hand side is not known and the left-hand side is known. So you have an equation with only one side and you want to figure out what that means. Now you can deduce network size from that one matrix by exploiting the fact that you have such an equation. So the framed equation up here The only fact I use now is that it is linear equation and that I do have an equality sign. So just the existence of this equation is informing me. And then I exploit a rank inequality. So I know that for any product of matrices, theta and x0, no matter what's in there, the rank of the product is at most the minimum rank of the two. Okay, the only thing mathematical advanced thing I use here. So if that is true, I check now the dimensionality of these. This is kn times n, kn times n, and n times n. Again, capital N is the number of units I have in the system. That's the quantity I want to know, which is completely hidden in here. It's not in here. K is the number of time points, and n is the number of components I measure. And now I evaluate, as I mentioned before, evaluate this rank equation with increasing number m of trajectories. And now I plot it relative to n for comparison. Of course, you don't know n before you do it, but retrospectively you can. And in a test case, you can always do that. The predictor, like the best prediction you get out of your thresholding, essentially as the rank of t, as a function of the number of experiments you take into account, and you see it just linearly increases up to some mistakes. Okay, it's like errors, which is due to real data. Okay, you have a finite sampling and so on. So nothing is exact. And then you see it saturates, and it saturates very nicely at n. So here is one, which is exactly n equals n. At this point, it saturates, and the moment it saturates, you know and the number of variables. And the interesting piece here is now that in systems identification and attractor reconstruction and so on, people had to stop for the curse of dimensionality at around 10, like dimensionality 10 or less. And we can easily go to 100, that's no problem. Now this is for linearized phase oscillator system. For the expert, that's a modification of the Kuromoto model, or an instance of the Kuromoto model. How do you practically detect it is an open problem. One way is to sort the singular values of the system. In a linear system, you get a large gap at some point because the rest is numerically essentially zero. But also in a nonlinear system, you get a reasonable gap. Mind the logarithmic scale here on the vertical axis. That's one way to find out. Of course, it's not 100% reliable, but it's a pretty good indicator. Now we go several steps away from our ideal case of a linearly stable fixed point. We go to nonlinear dynamics. And now we also go away from a fixed point. We don't even say Z star is any fixed point. It's just any point in state space where you assume there's sufficiently many data, okay? Somehow in this region, I have data, so I use these data. What we do know, if it's a system described by a flow, like a smooth flow, I have that the state of the system at time t is just the flow map applied to the initial state. So same problem as before, most of the Z components you don't measure. And now you take two trajectories, okay? You take two measurements and say, okay, compare two of these going by in my region of interest in state. Then you can linearize it. You get a linearization of the flow. Again, a reminder, you don't know the flow. And you project out those. And what you get is the same type of equation as before. I didn't say the same type of equation here as before, with theta ij now being this very abstract quantity. But it doesn't matter, right? It's just existence, as I mentioned before. There's a question by Rodrigo Migueles Ramirez. Do you want to speak up? I can't read
Yes. Hello. I don't know if you can hear me.
Yes, I can.
Okay, perfect. I'm just getting a little bit confused. I'm not super familiar with the nonlinear dynamics and so, but I'm trying to see if I'm grasping the main idea of what you're saying. So by looking at the, if I understand this properly, correct me if I'm wrong, by looking at the relaxation of the dynamics of each of the nodes that you can observe, you can therefore from there infer some information about what the topology will be of the network, right? So I'm trying to think what would be a case, because we're assuming that all of these variables are going to relax into a similar state. What would be the case in which they don't? Like, for example, if you didn't know beforehand, but some of the variables or some of the nodes that you can measure are not part of the same network as some others, and are completely separated so that their dynamics are not related with each other. Would you be able to tell that apart? And in that sense, would that be able to inform you about how far or how hardly connected they are between two modular, like in thinking of a modular network with only one edge connecting them, for example?
Yes. So in principle, like rigorous mathematics tells you that there is no way you can be 100% sure that you can make this statement. So you can't really distinguish. If you have, for example, if you record from two non-connected networks, that in any finite data set, there's some indication that there's correlation, for example, always. Well, except for zero measure time series sets. But you could think of tests, like statistical tests of identifying, but that's not the topic here. And also the second, or the first part of the question, or the first impression, it's not important that all my signals go to the same place, like here, okay? Like you see here, for example, they can go anywhere. And yeah. I quickly show in the next slide, like 2 slides from here, I will just show you another example where the entire thing is chaotic, so they diverge. It's not important that they go to the same point, or it's really only the fact that you have this form. Where is it? Yeah, this one. So this functional form, something like that. The only real condition you need is you have to have a linear form, a linear equation of this form, where theta is an arbitrarily complex nonlinear function of t and can depend on I and j as you like. But of course, now the more intricate question, which we didn't address yet, relating to your modules, for example, if some thetas could be very small compared to others, like it could be 100 times smaller, that's a different issue. And it's numerically hard to detect. Like even if you have good data, the pure numerics is super hard because you run into like determinant zero problems or related problems. But it is, so we could think of extending that and finding, for example, modules. You can just try to, okay, threshold that and say, okay, maybe it's not important. But the point here is really finding dimensionality. And you can't, in principle, you can't distinguish between two networks of 5 and one network of 10 rigorously. You can only make it statistically. So let's go on.
Yeah, thank you.
Welcome. So, and this translates now to, so this makes it even more general. It's nothing to do anymore with a fixed point or with anything of linearization, with linear dynamics. You just take your state space region of interest, and you, of course, you have to have some hope in the sense that they need to be close to each other in full state space, although the only thing you can observe is closeness in the projected state space. But apart from that, you get again the same nonlinear function here in an abstract way, in which gives you the same type of equation and therefore the same type of condition. And we applied this here, for example, to so-called Rössler systems, which are 3-dimensional units, and you couple them. And now we made it to just actually only record one of the variables in each unit, so you would deduce something different, but let's skip the details. So in a periodic system, you would see some relaxation, and they would become periodic finally, but they could also become non-periodic, for example, chaotic. So it's actually not important what the dynamics exactly is. The only importance is that near in your system, in your region of interest, you have sufficiently many data, which could be hard, but it's also not super hard, as you have seen from some of the presentations. Like how many data do you need? I go into detail here. So and then we tested it with noisy and heterogeneous and sparsely coupled networks. So sparsely coupled means most of the connections are absent. Heterogeneous means the weights are different. So these are now distributed on an interval starting from, I think, 0 even. And noisy means that in addition to that, to the randomness which comes from a structure, there's randomness in time, like external forcing, which you can't measure. You only can measure the variables of the system. And here, for example, you see, well, roughly it's the same thing. There are outliers, blah, blah, which is just a matter of presenting the right thing. Here you ask, how does it depend on noise? And the number of observations is in the hundreds. There is a discussion about, and we don't fully understand how the scales with the noise strength. It looks small, it's actually moderate, it's not super small, but it's also not as large as you might want it. That's actually like this one is reconstructible in the sense that if trajectories are deviating from deterministic trajectory like this one does, you can do that with the method. Part 2 is about finding topology. Now we think a bit differently, and we say, okay, let's start with a case where we can observe all the units, but you have no clue about the structure, like who is coupled to whom, and you want to know which of the other xj, which other components appear in the right-hand side of my nonlinear function for a given I, for a given node. You have a nonlinear network dynamic system. Again, you don't know f, and you don't know what's the structure. And what we do is we derive a linear system of constraints and then find a block, so-called block sparse solution to it. And I'll explain why we need that and roughly how we do it. To explain the structure of the equations, I take this very simple toy network, where at first glance, if you write down the equation and you're a mathematician, you think that, oh, they look the same, so they must be the same. But actually, as a physicist, you think differently about it, because these guys are, this one, for example, this function is coupling variable 3 to variable 1. So essentially, that's a two-pointed direction. Like you can think of a gravitational field or whatever, between units 3 and or from unit 3 to 1. And here the same from 1 to 2. But this one is different, although it looks the same, because here there are two different other variables, x1 and x2, acting on the rate of change of x3. So this is a genuine three-pointed direction. And if the first time when I talked to physicists, they said, oh, well, that's completely irrelevant. And I hope I can convince you that's not, because in biology, it's everywhere. Of course, it's an effective description, but that is what, for example, biophysicists do in terms of modeling. In graph theory, there's a notion of incidence matrix. The incidence matrix just encodes who is influencing whom, and they just row-wise identifies it. So 101 means the first variable, I have really problems seeing my mouse. The first variable is influencing variable 1, x1. The second is not. Now this is jumping away. The second is not, it's 0, and the third is again influencing variable 1. Here it's 110, and here it's 111. And the difference here, no 0 appearing, is because of this three-pointed direction. Now we introduce an artifact. We introduce something which you don't need if you ask different questions. We introduce a matrix. And the matrix is just formally thrown into the argument of the coupling function, f. And you introduce one matrix for each node. The nodes are labeled indexed I. So we introduce the matrix lambda I, which is a diagonal matrix if there's a dependence on node j, like for example here, node 3 is interacting with 1. you would have lambda 1 diagonal element 3, 3 being to be 0, and all the others to be to be 1 and all the others to be 0 except 1, 1. So here lambda 1, 2, 2 would be 0, and this just takes these rows and puts them as diagonals into a matrix. Okay, super trivial step. And I'm not saying we invented it. I also don't say it's anything advanced. I just say it's a cool trick because you put it in to then pull it out. Okay, next slide is showing how it works. So now we transform the system. Mind that we don't know f. We don't know capital F, and therefore we also don't know small f. And in addition, we don't know the lambdas. So what we did is a pure mathematical rewriting. And in first glance, it looks boring, but if you look at it, it's containing certain matrices which just project out the quantities you're interested in. So once you know the lambdas, you know the network. Okay. So it multiplies a system state on the right-hand side of the differential equation. It explicitly appears exactly once on the right-hand side, and it's closely related to the incidence matrix of graph theory. So it somehow makes a connection between dynamical systems description of a system and the graph theoretical description of a system. That's why we invented them. Jose Cardellego invented them to put in as an argument. Now you can go to, well, dynamic space, which is just state space plus the space of first derivatives. So for example, if you have two variables and you are interested in the rate of change of one of them, you would have a three-dimensional space. This two-dimensional subspace below here would be, well, state space, the full state of space of all states of the system, and then you plot the rate of change as a function of it. That's actually just representing this small f, okay? And of course, this in that space you have gradients, so you can ask when the rate of change is not changing. Now let's go back to this lambda matrix, the explicit dependency matrix. We take our unknown function and we expand it in terms of orders of interaction. The simplest case you can think of is you have one variable interactions here, two variable interactions here, three variable interactions here. And what if you expand it systematically, what you get is product of these lambdas, if you think about it. Okay, this coefficient here, the product of these two, is only non-zero if J and S simultaneously influence the rate of change of I. Okay, that's why you write it as a product. So you can formally expand that. Again, you don't know anything. You don't know F, you don't know G's, you don't know the lambdas, but you can write it down. Okay, it's a bit like in the first part of the talk. It helps you to write down the mass, although you don't know much about the details of what's actually going on. So the explicit dependency matrix naturally multiplies each dependency in each order, and it appears as linear coefficients to restrict the equations. Okay, so you see that just the fact that you expand it results in linearly multiplying these. So these guys appear as linear coefficients. The problem is that the G's you don't know. And one next step is to take basis functions and expand the G's and get basis functions. And the problem is which basis function. I'll come to that soon. But once you accept you have some basis function, you again get linear coefficients. They just multiply the lambdas, and you end up with a linear set of equations where you do know everything, because the h's, the basis functions here, you do know. The observed time series xj of t you have observed, so you can put it in, and then you know h of xj at each position in time, and you can estimate maybe the rate of change if your sampling is high enough. Okay, so now you have an equation where the only missing thing is a linear equation, and the only missing thing is a matrix of coefficients. And because of the construction here, this typical solution of them will be block sparse. You know, for example, if variable j is not at all influencing the rate of change of I, that will also be true in any combination with any s, any other variable xs. Okay, so if one of them is 0, the entire sequence is 0, and vice versa. If there's something present, then some of them are non-zero. So it's really like this. It's a block of relevant connections or coefficients and a large blocks of non-relevant ones, if you have a real network in the sense of not fully coupled network. And then we took ARNI, and you all know ARNI, to actually solve the problem, to find this block sparse solution. And ARNI is, of course, this guy. And the name is an abbreviation for algorithm for revealing network interactions. And what he does, he shoots down projections. So in simple words, I can't explain the mass details here, but in simple words, you try to find a good fit to your linear equation by just taking one, assuming that only one other node is influencing your node of interest, like say node I. Which one it is the one which best fits the linear equation, and you mark that. This is now the red guy. Okay, the red node is influencing node I collect red, and now I ask in the second step, if red is important, which second is the most important? And you can ask that by projecting out the contribution from the first one and asking the same question in a lower dimensional subspace. And you continue until you have a stopping criterion. The typical result you get is that the error function you measure, like the deviation of your data from the prediction coming from your reconstruction, drops off as an L shape with the number of terms you take into account. Here, for example, it decreases all the time, and at some point it settles up, and also it has less variance depending on what you do. This is for a system of k equals 15 neighbors, like interactions for each of the nodes, and the cutoff is like 16. So exactly it stops where it should be. So, and if it doesn't interact, there's no such L shape, just it continues gradually down without any indication. Now you can ask what the prediction, how performant is the prediction. And for that we use the AUC score, which is the area under the receiver operating characteristic curve, a measure of varying a threshold, how good it is. So again, don't go into details, but if AUC equals 1, you have a perfect prediction. If AUC is 1/2, it's like guessing. And you see here, so we have now a fake problem to test. The original model has two sign coupling contributions in terms of state differences with a phase shift here, and the next harmonics, like 2 times the state difference, added to that. So the total coupling function is this term. And we assume we don't know it, okay? We just measure the data, and now we take different kinds of basis functions. One is the class of powers of components. One is differences of components to some powers. Products of 2 components to different powers. Sine and cosine functions with prefactors, integer prefactor, and sine and cosine functions with differences of state variables and integer prefactors. And what you see is that in case B, C, and E, so for Z1, Z1, and Z1, performance is pretty well, so pretty good. So the algorithm works, and the entire method is operating and giving us the right structure. Whereas for the other two, it's not. So this tells us that only the type of function, of course, only an example, but we checked it extensively, only the type of function, not the function itself, is relevant for a successful reconstruction. So again, you don't need to know the exact function. As a matter of fact, we never put any phase difference here. Of course, you can argue that you can reconstruct it with E, but even if you take the class of functions B, so you have no clue about the interaction function here, you don't put any sine or cosine into your basis functions, you still reconstruct pretty well. Okay, that's case B. And now I would go on for 2 more minutes, I think. We just applied that to different model systems coming from biology. The first is the circadian clock of Drosophila. Here in a model with 10 units, and nonlinear coupling is essentially related to Michaelis-Menten kinetics. And the result is that it performs at least better than standard methods like correlation or transfer entropy, both of which are effective connectivities in the sense that they don't ask explicitly about questions about the differential equation, they just ask about some type of correlation, linear or nonlinear. And the second example system is the glycolytic oscillator in yeast, which is more interesting because it has both the standard pairwise interactions, indicated here by red arrows, and the 3-point interactions, like genuine 3-variable interactions, where 2 variables jointly, for example, S2 and S5, jointly influence the rate of change of S3. So we have 7 units, strongly nonlinear coupling, and true 3-point interactions together, together with the 2-point interactions. Again, the same result. The method proposed is strongly outperforming standard correlation-based methods, even the nonlinear correlation or information-based measures such as transfer entropy. Last slide. In my first part of my talk, I mentioned how you can infer information if you can only record a restricted number of units. And now we asked whether that is possible also for our recovery system. Of course, you can't expect to find links between units which you don't measure at all. But you can, of course, try to find links between those you measure. And this is an example. Oh, and in addition, we have a noisy system. So instead of the deterministic dynamics, which is plotted in the top panel on the right, you have a real dynamics which looks like this. So it's distorted. And here this is an example for a fraction of 40 out of 100 units observed with noise, and it's still reasonably performing. So AUC is not 90 or 95% that it was before, but it's still 80% and much better than, for example, correlation. So summary, how to find network size from only few nodes time series. It's an inverse problem, and we propose some black box approach. We arrange all the data we have, the maximum amount of information, in a detection matrix in a given way. We came up first with a linear system, and then we showed that it's not actually important that the system is linear. It's just important that you have sufficient data in a piece of state space you're interested in. And we employed, because it's simple linear algebra, we employed a basic rank inequality by sequentially considering an increasing number of experiments done for more and more time series. There are a number of open challenges. One is robust rank detection. So mathematically speaking, if you are a pure mathematician, you would tell me now that, well, given the rank inequality, it should be sufficient to record from only one node in a network of 1,000 nodes or 1,000,000, it doesn't matter. And that's true, but practically it breaks down for purely analysis, numerical analysis reasons, because detecting a rank in high-dimensional non-perfect data is a hard problem. So actually rank detection here is currently the bottleneck. how many nodes are necessary? I just mentioned it's one, but then the question is, given a resolution, what is a reasonable number of nodes? You can be sure that you actually get a reasonable result. What happens with multi-dimensional units? So say you have, for example, 3-dimensional units, but 3 variables per unit, but for each unit you can only measure one variable. And then you couple them in a given way. What happens? Yeah, and I mentioned the nonlinear approach, you're interested in some part of state space. Can you combine different parts of state space? That's the currently mostly focused on question in our team. Part 2, explicit dependency matrices, which you just formally write into equation, help to make the restrictions you get from arbitrarily nonlinear functions and systems linear, from which you want to find block sparse and block dense solutions. What I didn't show you is you can use the exact same idea for event-based time series. For example, if you're interested in spiking neural networks, you want to measure differences of event times where pulses, electrical pulses, are sent by the neurons. And formally, as you see, this equation here has the same form as the equation up here, and you can just put in your explicit dependency matrix in the same way and get the same kind of constraints. It's a bit more challenging because you get less information out of these spikes. Third thing we attempted, and well, it's not shown today, is what if you don't have the time information? So you don't have the timestamps to the data. You just get a collection, for example, because you measure histograms, or you have some cumulative experiments where you get a statistics of time series, but not the time series themselves. So you cannot correlate, for example, what the components, how they match in time. And that's relevant in systems where you do, for example, one or a few variables at a time, and then you redo this with the same, or a copy of the same clone of the system, redo it and measure, but you can't associate the timing anymore. And with that, I'll thank you for your attention, and I'm happy to ask more questions. There was one in the chat. Thank you.
Thanks a lot, Marc. That was really fascinating talk on this difficult problem of subsample networks. Are there any questions? There's one from Alexandre. Anmar has 2 questions. Go ahead, Anmar.
Okay. Thanks, Marc, for the very interesting talk. So the first question has 2 parts, actually. So maybe I missed it when you talked about the topology of the network. How do you choose the basis functions? You probably mentioned it, but I missed it.
Yes, important question, actually. So you have to click away my chat. It is not important. The only thing that is where
when you talked about the sine and cosine, that kind of that differential, yeah, exactly. So how did you're trying different ones here? How did you choose these?
Yes, so what you want essentially is a library of different types of basis functions, and then you want to check what the performance, like what the error measure is, which I presented on the previous slide. Like this one.
So for example, if you have, let's say, a Hodgkin-Huxley model, we're talking about like a model that we know already, and you're looking at the activation and activation.
Oh, if you know the model, that's much simpler.
Boltzmann functions. So how would you tell that this is covered by your bases, basically all these basis functions that you have?
Okay, maybe I didn't explain completely. So here, sorry, what you see here is that the performance for this model with these basis functions is good enough, say, or good for basis function class B, C, and E. So I don't need to know the model. That's the entire trick here, is that we don't know the model. If you know the model, I can help you with much simpler things. So here, the catch is you have no idea what the model is, and nevertheless you have to attempt to make predictions. And then, I mean, this is a performance, but you can also measure real, like only data-driven errors, which comes from the restricting equation. So you have a restricting equation, where is it? This one. right? You can choose coefficients and ask how well this with this.
I understand. I understand what you're trying to say, but the point that I'm trying to raise is that the nonlinearity that could be present in your dynamical system could be quite complex, and the basis functions that you have might be.
It doesn't matter. It does not matter. Well, of course, you can have, for example, stiff systems with fast slow dynamics. This is a different story. But if you have reasonable time scales of a given order of magnitude, details don't matter. The only thing what do you learn from BC and E here is that all of them are pairwise, like there are always two component variables which influence the variable I, okay? So somehow the only information I need, or I put in here, or I learn from testing it, is it is a pairwise influence. That's the only thing I learn, but also the only thing I need, because if I want to know the topology I don't care about the function, as long as I don't care about the function, I get the topology without knowing the function, but just testing, for example, single variable ones, this one or that one, you can come up with your own function. And all of those will not work. Whereas if the moment you put two component functions, they will work reasonably.
Okay, all right.
Of course, you can.
I have a second question, but I'll let other people to ask their questions. I don't want to take too much time. But thanks for the talk.
It's a question from Alexandre.
Yeah, it was actually very close to the previous question, so I'll let someone else go ahead.
Okay, Leon Glaston. Leon, are you there?
Yeah. Hi, Mark. So I was at a virtual meeting last week where somebody was talking about, I think, pretty much the same problem of how do you figure out the network from the dynamics. And she was developing techniques, which I have to say I didn't understand particularly well. And I have no idea how they correspond to yours. But she had a time series. I said, can you send me a time series? And I will see if I can figure out what the network is. And this time series was for 6 variables and about 30 data points. And they were oscillated. That was about 1 oscillation. So I don't know, using your methods with 6 variables and 30 data points, if I gave you that data, would you be able to use your methods and say, okay, here's the network. This is my best guess of what's happening.
I would doubt that anyone can do it.
Huh?
I would doubt that anyone can do it today, including whoever you spoke to last week. If you know the model, or if you have more information about the model class, it's a different story. But so our assumption again here is that we have no clue about the model. We don't know anything.
Okay, so for sure the model was a model similar to your equations. The equations of the models went by very quickly, but the model was essentially similar models in which there were Hill functions. Inputs from the Hill functions came from some subset of other systems. So it was very similar models to the types of models that I think you were showing, sorts of things that people do. It was a meeting about genetic networks. So we knew about the types of models in terms of Hill functions getting inputs from other variables in the network.
Yes, so but it makes a big difference. It's not so important what exact model generates my data, because it could actually be real data, so you don't have a full model. But it is important whether you know the model, like whether the information of the model is given to the guy who analyzes the data. If you're only getting the time series, or you get the model, for example, without parameters, yeah, that's a much simpler problem. If you're
okay.
If you one.
The model was essentially what I described, and I was able to deduce pretty well the network from the data that she sent by hand in about 30 minutes.
But true, but did you use the information that you knew the model? That's the question.
Yes, I know. I knew that it was differential equations of this form of where the interactions were via Hill functions.
So that, yeah, it's a different story. It's just a different class of problems. One is you essentially, I mean, it's of course a bit reduced in complexity, but essentially you fit an effective coupling matrix. Let's put it like simplifying. And in the other case, you have no clue about the model. You just, in one case, you know the model class, in the other case, you don't know the model class. It makes a big difference.
Okay, but can you just show your differential equations?
Which ones?
Well, just one of those simpler ones that you had. And
There's
not,
one up.
not for the Rossler equation.
No, there's one up now. Okay, that's a very simple one up now with two sine functions. And
No,
you know it's
yeah.
two sine functions.
Yeah, no, not that one. The one that had the interacting elements. One of the.
Like this one?
Yeah.
Yeah, the moment you know the functional form of the right-hand side, that's a much simplified problem. What we assume here is we have no clue about the equations, okay? Zero. We don't nothing. The only thing we have is time series.
So Leon, perhaps you could do this offline. There's two more questions.
That's fine, thank you.
Yeah, I mean, I suggested you could always get in touch offline. There's a question from Curtis. Should I read out the question, or can you want to ask it, Curtis?
Sure, go ahead.
Curtis wants to know how data hungry is the method compared to traditional methods like transfer entropy.
Okay, I can't say, because I mean there are scaling arguments, but here the comparison here is, so the green line is transfer entropy, and the other one is our method for the same data, like exactly the same data points. That's what I can say. So in a sense, it at least a good, but in general, I can't say. It's only because we have no full theoretical understanding. We know how it operates and we have intuition about it, but we have no proof like under which conditions it exactly works. This is also in part because of this somehow soft criterion where you break, where you stop, right? Yeah, but again, the stopping criterion is data driven. So I assume, given these curves, where are they? Given my curves, whoop, given these curves for all kinds, we have done that for like many systems, and they always look roughly the same. Given these curves, I would think it's about the same, like the same scaling, because we get at least into the same order of magnitude of quality given the exact same data. Is that
good, Curtis? Okay, so we have a last question from Michael Guevara. Michael wants to know, how does this approach compare with the method of Edward Ott to extract system equation from time series using reservoir computing?
Yes, I can't say. So we didn't do a direct one-to-one comparison with that work. But what I can say is the reservoir computing, sometimes my experience in other applications is sometimes it does work and sometimes it doesn't. The problem is you don't know when. So if you have a good idea of judging your results, maybe the reservoir computing approach is suitable as well, or possibly even better. But once you have no idea of how to judge it, I would think ours is superior, because you can more or less you can see a lot of things just from the data. And essentially, a reservoir computing approach is a black box approach, so you don't really see what's going on.
Okay, thank you.
There's a question from Rodrigo. He wants to know the references for the Drosophila and yeast papers, but perhaps he can just contact you for them, right? Maybe that works.
If you can, or you just look up Nitzan. Where is it? That's all. They are all the examples are in the Casadiego et al. 2017 paper, like this one.
That's great.
You can just write me an email as well. I just sent you the exact position. Yeah.
Thank you.
Well, I think we have no more questions. So thank you very much, Mark. Really inspiring and intriguing talk. Yeah, it really sounds like magic. I'll have to study the method better that you can record so many time series and get so much information about a large network.
Yeah, thanks.
Yeah.
Actually, my main motivation was, and also Jose's, was to solve this magic. Like, why is it? Like, even in the first part of the talk, I presented this dimensionality reconstruction. It looks like super magic because you hide. Imagine you have a brain. You measure from 10 neurons, and at the end, I tell you there are 10,570,000 neurons in your brain. Of course, well, practically it's not possible. Mathematically it's possible. And super, it's in the first moment, it's really magical in the sense it's counterintuitive. Like, it's not what you think.
Yeah, absolutely. Thank you very much for introducing us to this large area.
Me, and have a good day, I guess. For me, it's evening.
Yes, a day for us. Yes.
Thank you.
Thank you so much.
Bye, everybody. Alex, I'm